All right, lesson 1, change in tandem. So our learning objectives and skills are going to be to find the domain and range of a relation, to determine whether a relation is a function, find the domain of a function, evaluate a function using both explicit and implicit forms of a function, identify intervals of increase, decrease, or constants, find point of inflection in intervals of concavity, and find x and y intercepts. All right, function rules. A function is a mathematical relation that maps a set of input values to a set of output values such that each input value is mapped exactly to one output value. So what does that mean? That means that x cannot be repeated. Remember, a function, x cannot repeat. Okay, the set of input values is called the domain of the function, and the set of output values is called the range. And the rule of 4 concept will help strengthen your understanding for different ways to represent functions. And so you've seen this before, that there are 4 different ways to represent a function. We can represent it, 1, graphically, by points on a coordinate plane. We can make a table or a set of ordered pairs. Algebraically, we can write the equation in 2 variables, and in words by just verbally describing it. All right, so example 1 wants us, given this function, f of x equals 2x squared plus 5x, it wants us to evaluate, and we're looking for f of 3. So notice when we're looking for f of 3, if I write that above here, the only thing that changed is that where I had an x, I put a 3 in the place of it. And we all know it's what we do to the left side of an equation, we have to do to the right side. So it means on this other side here, everywhere we had an x, we're going to put a 3 there as well. All right, so for A, we know our problem was 2x squared plus 5x. So I'm going to make my skeleton here, which is just the numbers in the parentheses, no variables. And I know I'm going to plug in 3, so where I had an x, I'm going to put a 3. And then I'm just going to use PEMDAS to help me solve this. And so PEMDAS starts out with parentheses. Let me write it out. All right. So I do have parentheses, but inside those parentheses, I don't have anything to work. So no parentheses to work. E is for exponents, so I'm going to do my exponent first there. So I'm going to bring down this 2. 3 squared is 9. And I'm just going to bring down the rest of it. No other exponents. Then we're going to remember multiplication and division is on the same level. So if you have multiplication and division in a problem, you work it left to right, whichever one comes first gets done first. So we don't have any division, but I do have multiplication. So 2 times 9 is 18. 5 times 3 is a positive 15. And then we have addition and subtraction that's also on the same level. So we'd work that left to right as well, but all I have is 18 plus 15, which is 33, which is our answer. All right, for B, it says f of x plus f of 3. Well, we know what f of x is. That was given to us. So that's just going to be our 2x squared plus 5x. And then we have plus, and we know what f of 3 is because we just did f of 3 in part A there. So f of 3 is 33. And then we want to just simplify this if we can. Remember, this is just simplifying, so we don't need to factor unless it's a fraction in order to simplify it. So we can't combine any like terms, so there is our answer. C wants f of 2x. So we're just going to plug in 2x for our x. So I'm going to build my skeleton. So 2x squared plus 5x. And I'm going to replace that with a 2x. So this is going to be a lot like we did on A. Parentheses, there's nothing to work inside parentheses. Exponent, so I can do that 2x all of it squared. So I'm going to bring this first 2 down. 2x times 2x is 4x squared. Or because the parenthesis, the 2x there, does not have a plus or minus sign, we could also just distribute the square to both of them. That's different, though, if it had been 2 plus x. We wouldn't be able to do that. Plus or minus signs make it harder. So either way, I get 4x squared. And then I'm going to bring down the rest. We have our multiplication. So 2 times 4x squared is 8x squared. 5 times 2x is a positive 10x. And I can't simplify that any further, so there is my solution. D. D has a negative f of x. Well, that negative out front means we're just going to put a negative in front of all of our f of x, which was 2x squared plus 5x. And so we can take and just distribute that negative, and it gives us negative 2x squared minus 5x. Remember, putting a negative in front of everything just changes all of the signs. E is a lot like A and C. So E says we're going to take f of negative x, so we're going to plug in negative x for x. So I'm going to build my skeleton. I'm going to plug in negative x for x. Can't work parentheses, but I've got exponents. So I'm going to bring down that 2 in front. And negative x, all of it squared. Remember, that's the same thing as negative x times negative x. Or remember, anytime you take a negative number and you square it, it's always going to be positive. So I know that the negative x squared is going to become a positive x squared. And I'm going to bring down the rest. Then we have our multiplication. 2 times x squared is 2x squared. 5 times negative x is negative 5x. And I can't actually subtract them. They're not like terms, so I've simplified as far as I can. Let's see, and then example F, we have f of x plus 3. So it's kind of like A, C, and E. So we're going to plug in x plus 3 for x. So we have 2, I'll build my skeleton again, x squared plus 5x. I'm plugging in x plus 3. So I know, like I did earlier, there's no work to do inside the parentheses. X plus 3, I can't combine them. So I'm going to have to do exponents. Remember, squared means it's there twice. And because there's a plus or minus sign, that means we're going to have to distribute or do FOIL. So I'm going to write it out. So we have 2 times, I have x plus 3 here twice. And then I'm just going to bring down the rest of this. And then I'm going to go ahead and do my FOIL on these two. We have 3 things here being multiplied. So really I could pick any 2 and multiply, get that answer, and multiply it times the third one. But I'm going to go ahead and do my FOIL with these 2. And then I'll worry about the 2 here at the beginning. So I'm just going to bring it down. So when I do FOIL, I get x times x, x times 3, 3 times x, and 3 times 3. And I'm going to bring down the rest. And here we have a couple of different options of what we can do. But I'm going to go ahead and distribute this 2 at the front. And then I'm going to distribute the 5 in the second one. So 2 times x squared is 2x squared. 2 times 3x is 6x. 2 times 3x is 6x. And 2 times 9 is 18. And then I'm going to distribute that positive 5. 5 times x is positive 5x. And 5 times 3 is positive 15. And then we can simplify that. We've got some like terms going on there. So we're going to combine our like terms, and we're going to write them in descending order of the exponents. So start with your largest exponent first, which is x squared. And so all I have is a 2x squared there. Then I'm going to go down to x to the first. So I have a 6x plus 6x, which is 12x, plus 5x, which is 17x. So I have positive 17x. And then my constants, the ones that don't have an x, I have 18 plus 15, which is 33. I can't simplify that any further, so that is my answer. All right, moving on, we're going to talk about finding the domain of a function. So remember, if I give you a bunch of ordered pairs, or if I give you a table, or I give you a mapping, you can pull all the x's for your domain and all the y's for your range. But what if we have or even a graph? We can look at our x-axis to get our domain and our y-axis to get our range. But what if I give you an equation and no domain is specified, okay? Then the domain will be the largest set of real numbers, to which a value of f of x is a real number. But you have to be careful. You have to exclude any real numbers from a function's domain that cause division by 0 or that result in an even root of a negative number, that is, meaning an imaginary number. So basically what it comes down to is when we're looking at an equation that they don't give us a specific domain, the domain is all real numbers unless. And one of those things that'll keep it from being all real numbers is if there is a fraction. A fraction with x in the denominator, okay? If it's just a number on bottom, then you don't have to worry about it. But if x is in the denominator and it's a fraction, then you have to make sure that denominator cannot equal 0 because we don't divide by 0. Okay, so like if I have 4 over x, then I know I'm going to set the denominator not equal to 0 and solve. And so in this case, it would already be solved. And so I'd know that it's all real numbers except x cannot equal 0. And then I would just need to be able to write that in interval notation. The other thing to watch out for, too, is if we have an even root radical. So remember your even numbers, 2, 4, 6, 8, etc. And so if we have some type of even root radical, whether it's square root, fourth root, hundredth root, if it's an even root radical, we're going to take that root and we're going to set it greater than or equal to 0. Technically, it's the whatever's underneath the root here that has to be greater than or equal to 0, but it'll work out to be the same there, okay? Because when we take the square root of a negative number, we get an imaginary number. Or the even root of a negative number, we get an imaginary number. So therefore, it just has to be greater than or equal to 0. Now, some things to watch out for is sometimes they combine them, okay? So if they combine them and your radical is on top of the fraction, then you just solve them individually. So you would solve your denominator can't equal 0. You would solve the radical has to be greater than or equal to 0. I should say even root radical, has to be greater than or equal to 0. And then you kind of put those two things together to find where it actually is going to be, what makes both of them true. But the one I see confuse people sometimes is when it's a combination, but the radical is in the denominator. So like, for example, if I had 2x over the square root of x minus 3, okay? The 2x on top is no big deal. But the fact is we have a fraction, so we know our denominator cannot equal 0. And we have a radical, which our even root radical, which means that the square root piece there has to be greater than or equal to 0. But it's in the denominator. So even though it's the radical part says greater than or equal to 0, the fact it's a fraction says it cannot equal 0. So if you end up one like this, where there's radicals on the bottom, just set your radical greater than 0 and solve. And we'll see some of them coming up later, and we'll go more into it when we get there. All right, so just watch out for those things. All right, example 2 wants us to find the domain and the range of each relation below and to determine if that relation is a function. So remember your domain is your x's. And so for A, my domain would include 7, -3, 1, 3, and 2. None of those were repeated. Therefore, this is a function. My range is my y values. And so my y values include -2, 5, 6, -4, and then 5. But I already wrote 5 down, so I don't need to write it again. For B, B is mapping. And so we can see that our x's are on the left, our y's are on the right. And the arrows in between them tell us which x goes with which y. So because all of those x's are being used, we could say that that is our domain. All the y's are being used, so therefore that's my range. And is this one a function? It is not, because the x value of 2 has 2 arrows coming out of it, which means it's being repeated. So this is a relation only. So for C, C is a graph, and remember we said domain is our x's. And so I'm going to look at my x-axis, and we're going to have to write this as an interval because we can see that like -4, -3, -2 are being used, but so are all the ones in between them. And there's no way to list out every single number in between like -3 and -2. So we're going to use some intervals. All right, so when I look at this graph, we always write our intervals with the smallest number first. So my x's go left to right, and my smaller numbers are on the left. So when I look at this graph, I can see it starts right here when x is -3. X is -4. And then my graph keeps going to the right. There's an arrow there, so forever. So that means it's going to keep going till x is positive infinity. At the -4, it is a closed circle, so it's equal to, so we use a bracket. Infinity, well, what is infinity? We don't know, it just keeps going. So we can never equal infinity, so infinities always get a parenthesis. Then for our range is our y's. So my y-axis goes up and down, and we know we're going to write it as an interval. Therefore, we're going to start with our smaller y values, which is at the bottom. So the lowest point on my graph is right here, which is when y is -2. And then as I go on my graph, I can see it's going up. It's going up and up and up, and then it's going to keep going up. So the very top of my graph, it's going to go up to infinity. Again, infinities are always going to be parentheses. And at the -2 right there, we can see that that was a closed circle, so therefore it gets a bracket. And is this a function? Yes, it is. None of my x's are repeated. And then we have D. So be careful on D. In D, we have a couple things happening. I see these dashed lines, which remember, this one means there's a vertical asymptote there. This one means that's a horizontal asymptote right there. And then be careful because right here we have a hole in our graph. Okay, it's just a gap, it's a hole. All right, so for my domain, my x's, I'm going to start on the far left, which I see there's an arrow there, which means it's going to keep going to the far left. So that number that's way out there on the far left is negative infinity. And so as I come along my graph, I'm going, and then I hit that hole right there when x is 2. So I'm going to have to stop. So it's going to go from negative infinity to 2. Negative infinities always have parentheses. We can't equal them. And the 2 is an open circle, which means it's not equal to, so I'm going to use a parenthesis. And then I'm going to put a union symbol. I'm going to jump over that hole. I'm going to start right there on the other side of it, which is not at 2, but it's that very next number that we can't actually put a digit down for. So again, we're going to use the 2, but we're going to say it can't equal it because it's an open circle. So we're going to use a parenthesis. And then it's going to keep going up. And it's going to get closer and closer and closer to that vertical asymptote until it jumps on the other side of it, which we're back down here at the bottom. So it's going to keep going until it gets to the 4, which is where the vertical asymptote is at. And then it's going to jump. Vertical asymptotes, it will never equal, so we're going to use a parenthesis there. Then it's going to jump to the other side of the 4, but we're still going to say it's going to start at 4, but it's not equal to it. And then as we come here, it's going to keep going to the right, so it's going to keep going to positive infinity. Infinities always have a parenthesis. Then, for my range, my y values, remember your smaller y's are at the bottom of your graph. So I can see it keeps going down, and it keeps going down to that very bottom y value, which is negative infinity. Infinities always have parentheses. And as we come up, we're kind of curving off here. We're going to still keep going up until we get so close to that horizontal asymptote, but we're not going to cross it there, okay? And so we're going to keep going up, and we're going to get super close to that -2, but we're not going to cross it. then what's going to happen is we get so close to it, it's going to throw us up here, which is on the other side of it. So then we're going to go from that -2, and we're going to go up here till we hit that hole again, which is at y value of 5. And then we're going to jump on the other side of that hole at 5, and we're going to keep going up, and so we keep going up to positive infinity. All right, example 3 is to define the domain of each of the following relations. Is the relation a function? Use a graphing calculator to verify your findings. All right, so on A, here we have f of x equals x squared plus 3x. So let's see, we're able to, there's different ways to do it besides just using a calculator here. Whoops, sorry. All right, so let's see. So I can pull some points here. Excuse me, I am so sorry. All right, so let's see, we have x-intercepts at -3 and 0. Somewhere in here is my vertex. I know it's going to open up because it's positive. I'm just kind of using some stuff I already remembered from Algebra 2 to help me graph it, but if not, you can put it in your calculator for right now because we haven't talked about how to graph them without one yet. All right, and so I'll look at this and I can see that my domain, my graph, if I start on the far left there and go all the way to the far right, it's going to be -infinity to infinity. And then my range, my graph, the lowest point is actually at -2.25. Using my calculator to help me there, and it's equal to it, and then it keeps going up to positive infinity. And we can tell then that yes, this is a function. 1, because I was able to type it in y equals in my calculator, only using y1. Second thing is it passes the vertical line test. All right, for B, at this point, to be honest, I would use my calculator to kind of just help me through this. And so at B, we're going to have a vertical asymptote at -3 and +3. And we have an x-intercept at 0, 0. And so I can see that my graph is going to look something like this. And also have a horizontal asymptote. Oops, that looks really bad. I'm sorry. I have a horizontal asymptote here at y equals 0. All right, so we got our graph here. And this is one of those that I was talking about the other day in class when we went over, if you were in class, that you can cross a horizontal asymptote, but only in the middle of it, okay? We'll talk more about horizontal asymptotes, but they're dealing with the end behavior. So down here at the very far ends is where it'll never cross, but it could cross in the middle like this one does. All right, so when we go through to do this, we get our domain. So starting at the far left, I can see it keeps going. So it's going to be -infinity into that first asymptote at -3. Can't touch it because it's an asymptote. Union, that asymptote to the next asymptote. So -3 to +3. Union, and then the other side of the 3 goes on to infinity. And then we have our range. Range is the y value. So we start at the very bottom, which it keeps going down. And it keeps going up. There's nowhere in between that it cannot be, because we actually right here, we cross that asymptote. So it's going to be -infinity to infinity. You know what? I drew that backwards. I am so sorry. That middle part is not correct, and I am not starting this video over because of that piece. some reason I just drew it backwards there. This should go like this. I apologize. I hope you caught that. All right, C. C is a square root function. It's got a reflection, some shifting and stuff going on. So let's see, it's going to look something like, got a point here, we have a point up here. So it's going to look like this. So for my domain, I can see the x's, it keeps going to the left, so negative infinity. And it keeps going all the way into that far point on the right, which is when x is 2, and it's equal to at the 2. It's got a closed circle. My range, my lowest point on this graph is 0, and it's a closed circle there, so it's equal to. And my graph keeps going up, and it keeps going all the way up to positive infinity. Infinities always have a parenthesis. And this one is a function. Now, I forgot to ask on B, was B a function? B is a function. It's a rational function. A was a quadratic function, B was a rational function, and C is a square root function. And what about D? D is going to be easiest for us to be able to put in our calculator if we solve it for y. Well, we're going to have to solve for y in order to put in our calculator. So let's work on that. So let's move the x squared over. So I'm going to subtract x squared. So when I do that, I get negative y squared equals 4 minus x squared. And then I'm going to divide everything by negative 1. And so I get y squared equals negative 4 plus x squared. And then to get rid of the square, I have to take the square root of both sides. Now be careful, because this is where mistakes are made. Remember, when you take the square even root of something, you always get plus or minus. So we got plus or minus the square root of negative 4 plus x squared. Now, if I want to put that in my calculator, I don't have a plus or minus button, which means that I'm going to have to use y1 and y2. So in y1, we would put either the positive or the negative square root. So I'm just going to put the positive one. So negative square root of negative 4 plus x squared. And in y2, I would put the negative square root. So the negative square root of negative 4 plus x squared. And then I can graph it. If you have to separate it into y1 and y2, I'll tell you now, that means that it's not a function, okay? If it has y squared in it, it is not going to be a function because of the plus or minus. The same thing with the absolute value of y. So those two things in equations make them not a function. All right, so when I go to graph this one, let's see. It's actually going to look like two parabolas turned sideways. So I got one that's looking something like this, and the other one that's looking something like this. Okay, and it should be about equal width there. So seeing that, I can see that my domain, it does keep going to the left. So we're going to start at negative infinity, and it goes all the way up to the negative 2 where it's equal to, and then it's going to jump over to positive 2. So we're going to put union, and then we're going to go to positive 2 where it's equal, and it keeps going to the right to positive infinity. And then for my range, my graph does keep going down, and my graph keeps going up. So, and there's no breaks or anything in between it. So we're going to start down at the bottom at negative infinity, and we just keep going all the way up to positive infinity. And is this a function? No, it is not. This is a relation only. And we can tell that. I already kind of hit on it. One way was because we had to put it in y1 and y2 to look at our graph. And the other way to tell is if I use that vertical line test, it touches in more than one spot, therefore x is repeated, and it is not a function. All right. So in general terms, we can say that a function increases over an open interval of its domain if the graph rises from left to right on the interval. Likewise, a function decreases over an open interval of its domain if its graph falls from the left to the right on the interval. Finally, a constant function over an open interval of its domain if its graph is horizontal on the interval. All right, so if it's going, as you read your graph from left to right, if it's going up, it's increasing, going down, it's decreasing, and if it's staying the same, then it's constant. It is important to note that the intervals refer to the x values where the y values either increase, decrease, or remain constant. So we always label it by our x values, okay? The y's are what's increasing, decreasing, or staying constant, but where is it happening? We always tell where something is happening by those x values. All right, and so your definition of increase or decrease or constant is basically just what we said. It's a little more formal. Remember, if it's going, as you read your graph from left to right, if it's going up, it's increasing. If it's going down, it's decreasing. And if it's staying the same, then it's constant. All right, so consider the function y equals g of x shown at the right here and trace each interval where the function behavior is, where it is increasing. And it says to do this in green. I don't care if you use colors or not. I'll try to go with the colors here. So where is it increasing? So as I look from left to right, I want to know where is it going up. So right there it's going up, and that's the only place. So it is increasing from -2 to +2. Now this is something that's changed. I'm not sure. I'm sorry, I lied. That's 0 to +2. I looked at the y value there, and we always label by our x's. All right, so from 0 to 2. Now, I'm not sure how the Algebra 2 did it last year, but I know if you had me for pre-cal last year, we talked about that they're always considered open intervals. But for AP pre-cal, their definition includes the endpoints. So we are actually going to use brackets when we talk about increasing, decreasing, or constant. Okay, the only time we don't use a bracket is if it is an infinity. All right, where is it decreasing? It wants us to use red to show that. So we are decreasing right here, which is when x is -infinity all the way to where x is 0. So -infinity to 0, and we're going to use that bracket. And then we're also decreasing right here where x is 5, all the way to the right, which is where x is +infinity. So x is 5, all the way to +infinity. All right, and where it's constant, it wants us to use yellow. So we can see that right here, this piece here, from 2 to 5, we are constant. So from 2 to 5. It's a little harder to see. All right, state the domain. So our graph keeps going to the left, so it's going to start over at -infinity. And as I trace around that graph, there's no holes, no gaps, anything like that. Keeps going to the right, so therefore it keeps going to +infinity. My range, the lowest y value, it keeps going down, so the lowest y value is -infinity. And again, there's no holes, no gaps, no asymptotes, anything like that. Keeps going up to the top, so it's going to go up to +infinity. All right, then F says, what thoughts do you have about intervals stated above? Did you use brackets, or closed or included points, or parentheses, open or non-included points? Why or why not? All right, so brackets are used for intervals of increase and decrease as they are closed intervals. So brackets are used for intervals of increase decrease, or constant as they are closed intervals. All right, and that is the end of the first part. So I will make a second video with the second part of it.